Around 1861 until 65, James Clerk Maxwell published some papers that talking about electromagnetism. In our mathematical language today, the core of paper published is about these four famous Maxwell's equations. The first one is about divergence of electric field, and here is about divergence of magnetic field, and so on for the curl. The derivation of these four you can check in my video about electromagnetism playlist. In this video, we will learn about these four Maxwell's equations, that these equations has Nabla kind operators such as divergence and curl that lead us to what we know about differential equations. In study of differential equation, we commonly know that differential equations, especially in partial differential equation, it has initial conditions for time part and has boundary conditions for space part. So that's why these equations need conditions to make the solution clear. But how we construct these conditions? In this video, we will discuss about boundary condition, which is condition in space region. First, suppose we have a surface just like this, that we can extend this surface maybe infinitely wide, and in the center of the surface, we can imagine there is a pillbox just like this, or known as Gauss pillbox in graphite, that this pillbox we squeeze so we can have locally flat surface inside the box. Next, in electromagnetism, this surface split to regions such that the upper region has mu1 and epsilon1 as permittivity and permeability, and so on for the mu2 and epsilon2. By this setup, we can check the pillbox by zooming out so we can have this box as the surface inside is flat. In general electromagnetism, electric and magnetic vector field may go out, go in through this box. So that's why in divergence case, we have this divergence for electric field, and here I forgot the epsilon 0, so I was including the epsilon 0 inside this row, which row here is about electric charge density inside this pillbox. And after that, about the divergence of magnetic field, of course always equals to 0. By divergence theorem, we can replace this differential form as integral form, which we replace the rho as total electric charge over epsilon 0 q total. And by these two in general, we will have this set of equations, which for electric field part, we will have this integral that explain left-right surface is equals to forward-backward surface, and then it's equals to 0 when we set the volume as small as possible. Why? At this integral, we see that in surface before, even if we squeeze as small as possible of the surface, does not change the characteristics significantly. This integral property contrary with up-down surface. So that's why in this case, we focus on up-down surface such that we have this remain equation which n hat here relate to surface vector direction, here minus because of the difference of up and down, and this equality will become as this, which the sigma here is about charge density at surface boundary. And by removing the integral, we will have the equality is about this, and that's for electric field condition. For magnetic field condition, with the same procedure as before, we will have the final result is about this equality. So that's why these two equality is about boundary by divergence part of the equations. Then the second, which is the last part here, we suppose again the surface, but now we create a loop of vector field just like this that passing through the surface. If we imagine as before, the different medium and this vector field may be electric and magnetic field, we can have next boundary condition by curl equations. And using these curl equations, suppose that we label this part as L1, this part as L2, this part as L3, and then this part is L4. And by this condition, we can turn this curl equation, of course by Stokes' theorem, as counter integration, such that this counter integration, just like before, which here we said that L2 and L4 approach to 0 when we squeeze the surface that bounded by the loop. So that's why we have this remaining integration. For Faraday lens, we will have this integral equation, and for Ampere-Maxwell, we will have this long integral equation. Notice that the K here is about current density along the integration. Then, if we collect this equation, there are remaining integrals such as these two that make this condition complicated. And of course, we can fix this part that we squeeze the surface as small as possible. So that's why these two parts will approach to 0. And then at the end, we will have these two sets conditions come from boundary by the curl. And after we collect these four, we will have boundary condition for electromagnetism in Maxwell's equations. And that's how we formulate boundary conditions of Maxwell's equations. I hope you enjoyed this video. If you like this video, don't forget to share, subscribe, and turn on the notification. If you have any requests and questions, write down the comment below. And that's it. Bye-bye.